Hello everyone, and welcome to the first episode of my YouTube series on lunar exosphere studies. This is DUMLUPINAR, and I am a graduate researcher specializing in the dynamics of the lunar exosphere and lunar sodium tail. Through this series, I will be reviewing key scientific papers that explore the presence and behavior of volatile elements, especially sodium and potassium, in the Moon's tenuous atmosphere. So, these elements provide valuable insight into space weathering, meteorite interactions, and the Moon's unique exospheric processes. In this first episode, I will be reviewing the paper Meteoric Influence on Sodium-Potassium Abundance in Lunar Exosphere measured by LADEE by Dr. Jamey Szalay from 2016. So this study, based on the data from NASA's LADEE's mission, examines how meteorite showers, and particularly the Geminids, affect the lunar surface and exosphere. So let's dive into this fascinating world of lunar exosphere dynamics and uncover how external forces shape the Moon's atmospheric environment. So, as I said, this presentation summarizes a paper that analyzing the impact of meteorite activity on the lunar exosphere, particularly focusing on sodium and potassium abundances. So observations were conducted during NASA's the Moon mission LADEE, which is Lunar Atmosphere and Dust Environment Explorer mission. The mission's unique combination of instruments allowed for unprecedented insight into short-term and long-term variations in the lunar exosphere during the meteor showers. And the Lunar Atmosphere and Dust Environment Explorer LADEE orbited the Moon for approximately about 6 months, and taking data with the Lunar Dust Experiment and LDEX, ultraviolet visible spectrometer UVS, and neutral mass spectrometer NMS. Here they compare coincident LDEX measurements of meteoric influx to exospheric column densities of sodium and potassium derived by UVS. So they report a strong correlation of exospheric potassium and meteoroid ejecta during the Geminids meteorite shower, so exhibiting a much stronger response than sodium for about potassium. So with exception of Geminids, we find a weak correlation between the sporadic meteoroid influx as measured by LDEX and exospheric densities as measured by UVS in the paper. So let's begin. For introduction part, key concept: the Moon has a tenuous exosphere composed of neutral atoms, charged particles, and dust ejecta. So the Moon's exosphere provides valuable insight into surface exosphere interactions and space weathering. And sodium and potassium are particularly useful as tracers because they respond to external stimuli such as solar radiation and meteorite bombardment. So while previous studies highlighted their presence, mission LADEE's, the Lunar Atmosphere and Dust Experiment Explorer, the Moon's mission, high-resolution observation offer a detailed understanding of their dynamics. And for background and key findings, sodium and potassium originate from a mixed source, each contributing differently to lunar exosphere. Discovered of sodium and potassium exosphere was in 1988 by Potter and Morgan. And since their discovery in 1988, sodium and potassium have been used to model exospheric dynamics. So their sources, photo desorption, impact vaporization, and thermal desorption, compete with Low's mechanism like photoionization and genes escape. So the key takeaway is that meteorite showers, particularly the Geminids, have a measurable impact on potassium, whereas sodium exhibits a much weaker response. So the paper's critical finding especially is that potassium surged for 4 to 8 days after the Geminid meteorite shower, while sodium showed minimal response, as we said. And this disparity suggests potassium interacts more complexity with the surface, possibly due to longer residence times in regolith grains. So the weak correlation between sporadic meteorite impacts and neutral abundances suggests additional governing processes. So yes, we can say maybe surprisingly sporadic meteorite influx showed a weak correlation with abundance. But this implying other processes dominate under non-shower conditions. So this means understanding the lunar exosphere response to meteorite activity is crucial for future missions, especially those studying surface composition and space weathering. This research also helped refine model predicting exospheric behavior. In this paper, the authors have their goals were threefold. Correlate meteorite influx with sodium potassium abundance shifts, compare short-term shower-driven versus long-term sporadic variations, and explain different responses between sodium and potassium. So this work is just academic. It is not just academic. It informs lunar mission planning, helping predict how atmospheric volatiles might affect instrumentation or in situ resource utilization. For example, understanding the potassium persistence could aid in designing systems to harvest surface materials. So methodology, LADEE's instrument synergy was pivotal here, and we have its figure here. LDEX detected meteorite impact minutely period, and UVS tracked sodium potassium column densities twice a day, and NMS provided compositional contact. And by focusing on Geminid, high velocity meteor shower with predictable timing, the team isolated cause effects relationships. For instance, LDEX dust impact rates were cross-referenced with UVS spike in potassium density, ruling out solar radiation as the primary driver. This multi-instrument approach minimized ambiguities inherent in exospheric studies. For example, let's dive into the results. Figure 1 in the paper provides a broad overview of the impact of meteorite showers on sodium and potassium densities. LDEX measures meteorite influx while UVS tracks exospheric column densities of these elements. So we see that potassium exhibits a stronger and longer lasting response to meteorite influx, while sodium shows weaker contours indicate error margins, confirming the robustness of the observed trends. Here, Geminids has pinned on this line. The Gemini shower is particularly notable for its sharp increase in potassium abundance, lasting several days beyond the peak flux. So let's unpack figure 1 more, which integrates LDEX meteorite influx data with UVS derived sodium and potassium column densities, as I said. Here the green lines show raw LDEX impact rates 1 day average and UVS abundances, while the black lines represent smooth smoothed 4-day trends to filter out short-term noise. And the gray contours highlight 1 to 4 sigma error margins, ensuring the trends are statistically robust. So for takeaways, key takeaway, potassium orange curves surge during the meteor showers. Here, these orange curves surge during meteor showers like Geminids, vertical lines with enhancement persisting 4 to 8 days post-shower, and about sodium, which is also blue line you can follow, however, shows only weak fluctuations. The orange bars mark when the moon was in Earth's magnetotail. Here, these orange bars as marked when the moon was in Earth's magnetotail shielded it from solar wind, but not that potassium spike aligns with meteor influx, not magnetotail entry. So this confirms meteorite bombardment, not plasma shielding, drives potassium variability. So we will also see its figure, what I mean by visually Earth's magnetotail about when moon passing through in this passage. So here we have quick pause for the presentation about the paper for this, because before we continue with the paper results, now I would like to briefly go off the record to show you a schematic figure illustrating the moon's position within Earth's magnetotail here, which figure right there is not belong to the paper. Okay, so this will help clarify some concepts related to exospheric dynamics. The orange bars here, figure 1 left, represent the period when the moon inside Earth's magnetotail, like right side, the orange passage here, typically for about 5 to 6 days during each 27.3 day lunar cycle, and around the full moon phase here. Unlike Earth, the moon lacks both an rich atmosphere, as you know, and the global magnetic field, leaving it fully exposed to space weather's effects, such as the solar wind, and when it's outside in the magnetotail. However, what's important to note here is that potassium abundance spikes in the lunar exosphere do not align with the moon's entry into the lunar magnetotail. Instead, these spikes are closely tied to periods of meteorite influx, such as during the Geminid meteorite shower. So this observation confirms that the meteorite bombardment through mechanism like impact vaporization rather than plasma shielding from Earth's magnetotail is the primary driver of potassium variability in the lunar exosphere. Now let's get back to the paper's other core findings. So as we said, figure 1, why this matter? Potassium's prolonged response suggests it's temporarily retained on the surface, for example, trapped in the regolith grains on the surface before re-release, whereas sodium escapes faster. It will be. So this divergence hits at elemental differences in surface interaction physics. So figure 2 examines how sodium and potassium abundances change over time relative to lunar phase. The radial extent and the color coding in the graph illustrates the evolution of these elements in the exosphere. The orange region show periods when the moon was inside the Earth's magnetotail, as we said before, possibly shielding the exosphere from direct solar wind interactions. The phase-dependent variations provide critical context for understanding how external influences like solar radiation and plasma interaction or affects the lunar exosphere. Maybe we can consider cosmic galaxy rays. So as we can see, figure 2 reveals how sodium and potassium abundances vary with lunar phase over January to April 2014. So the radial extent and color gradients, cool to warm, illustrate density change. Maximum abundances occur near sunrise, right side, and sunset, left side. So driven by radiation diurnal cycle. And the orange regions correspond to magnetotail periods, which we saw approximately plus to minus 30 degree from full moon. And surprisingly, potassium abundance, which is here blue line here, and potassium increases even under magnetotail shielding, implying meteor impacts, not solar wind sputtering, dominate its dynamics. So, however, sodium, shows phase locked behavior tied to solar photon stimulation. So, as summary, key insight. Potassium phase independence and correlation with meteorite showers highlights its unique sensitivity to impact vaporization, unlike sodium, which is more responsive to solar-driven processes. So, let's say again off the record, my comment about that. This will be, as we said, need more study. Maybe it need more studied for about sodium lose escape mechanism, which is also I would like to record another video for you for this topic. And yeah, figure 3 isolates the Geminids effect from the, as we saw before, figure 1. Here figure 3 is isolated. The first and third rows shows sodium potassium column densities, which is black lines, against synodic average, green. And the second and the fourth rows display residual after removing synodic trends, synodic moon trends. This strips out regular solar-driven variations, isolating meteorite-driven changes. So, post-Geminids, potassium residual, which is black dots, spike sharply, lingering for days. Sodium residuals barely budge. The bottom panel, LDEX impact trace, confirms the timing the Geminids intense influx, which is gray bars, align perfectly with potassium surge. So, critical implication, potassium's persistence suggests two-step processes: impacts vaporized surface materials, followed by gradual thermal or photon-driven release. So sodium's lack of response may stem from faster photoionization or weaker surface bonding. So figure 4, which is quantifies potassium's decay after the Geminids. The authors decided to go with only for potassium because, as you saw here, there is no exact response for sodium. So for potassium, The black line shows residuals, while colored lines model decay rates. The best fit 4 to 8 days persistence aligns with LDEX meteoroid flux, which is gray line, confirming that freshly delivered potassium lingers on the surface before escaping. So yeah, you can ask why for 4 to 8 days question. Yeah, this time scale matches regolith gardening processes. Micrometeorite impacts or thermal cycling could liberate trapped atoms over days. And sodium's absence here reinforces it shows shorter surface residence time, likely due to weaker adsorption of faster ionization. So broader impact, this decay rate informs models of volatile retention on airless bodies, crucial for predicting water volatile resources for future lunar bases as Artemis mission upcoming. So finally, figure 5. Figure 5 integrates data from multiple sources to compare potassium surface abundance with exospheric density variations. The Lunar Prospector mission provided gamma-ray data on potassium distribution, which aligns well with UVS measurements. The impact angle analysis shows how the Geminids and Quadrantids meteorite shower deposit material differently based on their entry trajectories. Left side Geminids and here Quadrantids. These findings indicate the exospheric potassium mobility varies across different latitudes, possibly influenced by surface temperature, regolith properties, or local electric fields. So figure 5 breeds surface and exospheric potassium. As you can see, the top panel overlays UVS column densities, colored dots, and on Lunar Prospector surface potassium map grayscale. And despite scattering surface deposits, exospheric potassium shows latitude-dependent mobility, peaking near the equators. Yeah, near the equator, as you can see. So the impact angle contours, which is Geminids solid lines, Quadratids dotted, reveal the steep Geminid impacts near the subsolar point, maximize vaporization efficiency. The bottom panel compares normalized surface, which blue lines, and exospheric, which is black and green lines, potassium, exospheric potassium, showing tighter correlation post-Geminid crosses. So takeaway, potassium exospheric abundance is not just about surface concentration, it is shaped by impact geometry, local temperatures, and possibly electric fields that enhance mobilization at certain latitudes. So, before we move into the discussion part, let's summarize the key findings from results. So first, potassium exhibited a strong and prolonged enhancement following meteorite showers, particularly the Geminids, persisting for 4 to 8 days. This suggests that potassium atoms spend much of their lifetime on the lunar surface, shielded from UV radiation, before returning to exosphere. This aligns with previous finding by Sprague et al. 1992 and confirms that impact vaporization plays a significant role in potassium exosphere behavior. So additionally, sodium does not show a similarly large response despite having a nearly identical photoionization lifetime, which is 0.6 days for sodium versus 0.4 days for potassium. This suggests that the sources and sinks of sodium and potassium are significantly different, potentially due to different retention or chemical interactions with lunar regolith. And LDEX impact rates strongly correlate with UV sodium and potassium densities, reinforcing the meteoroid-driven impacts. Vaporization is a primary mechanism for potassium enhancement. However, the moon passage through Earth's magnetotail does not have a strong influence on potassium variability, ruling out plasma shielding as a dominant factor. And these findings set the stage for further discussion of the implications. So now that we have reviewed the key findings, let's discuss their broader implications. One of the most significant takeaways is the potassium remains on the lunar surface longer than expected, as we said before, expected before being re-emitted into exosphere, with an estimated 4 to 8 days surface residence time. So this means that potassium atoms are not immediately lost to photoionization, but instead undergo temporary retention, possibly in cold surface traps or weakly bound states. In contrast, sodium does not exhibit the same prolonged retention behavior, since sodium and potassium nearly identical photoionization lifetimes. This indicates that their sources and sinks must be fundamentally different. So understanding these differences is key to refining lunar exospheric models. So this study also found that outside of the Geminids, no strong short-term relation exists between impact rates and exospheric densities. However, there is a weak correlation on the scale of lunar phase, possibly influenced by variation in radiation pressure or other synodic effects. So, and the UVS data also showed a strong correlation between surface potassium abundance and exospheric column density, confirming that surface-bound potassium acts as a reservoir for exospheric potassium. And if potassium had a much longer lifetime, we would expect a more diffused exospheric distribution rather than a close tracking of surface sources. So these findings have critical implications for future lunar exploration and planetary science. Understanding how meteorite bombardment affects exospheric species is crucial for predicting volatile behavior, space weathering processes, and potential in situ resource utilization strategies. And future missions, including those studying volatile transport and exosphere surface interactions, can build upon these results to refine our understanding of airless body atmospheres. Further modeling and observational studies will need to fully unravel why sodium and potassium respond so differently to intense meteoric bombardment, and why only selected meteorite showers appear to play a major role in potassium variability. And thank you for watching. As we wrap up this first episode of Lunar Exosphere paper review series, we have explored how meteorite showers, especially the Geminids, play a crucial role in shaping the moon's exosphere, particularly in the case of potassium and sodium. We have seen how impact vaporization rather than plasma shielding is the primary driver of potassium variability, and how sodium and potassium respond differently to external influences. So understanding these dynamics not only helps us refine models of lunar exosphere, as we said, but also depends our knowledge of how airless planetary bodies interact with their space environment. So these insights are essential for future lunar exploration, from scientific missions to resource utilization and even long-term human presence on the moon. I hope one day. So thank you for joining me on these deep dive into lunar exosphere studies. If you find this presentation valuable, don't forget to like and subscribe, and stay tuned for more episodes where we will continue to explore volatile elements and their role in Moon's tenuous atmosphere. So, and always, my motto: peace at home, peace in the world, peace in space.